Our next panel talk will be given by Professor Rachel Grange. She from ETH Zurich, Switzerland. She studied on the integrated opticals and the nonlinear nanophotonics with metal oxide for classical and quantum device. Today we will talk about geodetic nonlinear nanomaterial for on-chip classical and quantum device. Let's warmly welcome.
Thank you very much for the introduction. Good morning, everyone. Indeed, I'll be talking about Ki2 material, and half of my group is working on top-down crystals for integrated circuits. But here, I will mainly focus on top-down crystals for flat photonics, as well as our development of bottom-up sol gel for simplifying the fabrication, and on single nanowire or single nanostructure that you can use for generating directly entangled photons on the chip. So this is my team, the Optical Nanomaterial Group at ETH Zurich, and we are focusing, and our motivation is to the fact that there is a lack of scalable platform with nonlinear, electro-optic, and quantum features at the same time. And the applications are really broad, right? You want to have data transport that goes very fast. You want to have sensing very broadband. So we have a project where we are trying to do detection of atmosphere of exoplanet in the mid-infrared. So quantum sources as well that are on chip, that are not relying on too low temperature, as well as optical computing. And for optical computing, you need nonlinearity and also a lot of modes available with those nonlinearities. So currently, our setup still look like this, so difficult to send it to space or under the sea. So what you want to have is to find out about a platform that is integratable, that can do all this generation, routing, processing, modulating, and detection on a chip. And the current platform that we've seen many examples at this conference are silicon photonics, silicon nitride, or titanium dioxide, either for photonic integrated chip that are now not only in the research, but also in companies for quantum computing, and of course for flat photonics, the example of metasurfaces. All those materials are centrosymmetric. And the one I am interested in are non-centrosymmetric, such as barium titanate, lithium niobate, and also gallium arsenide. I will mention example with those three types of material. So what are the missing properties of silicon, silicon nitride, titanium dioxide? First of all, frequency conversion. So if you want to have photons, like those pump photons at 800 nanometers that can be transmitted very efficiently either on chip or on flat photonics. And I will still mention a bit photonic integrated circuits here. Here you have an example of a pump photon at 800 nanometers, which generates a very strong a very strong second harmonic generated photon thanks to periodic polling. Because of course, when you go on chip, not on flat photonics, right, you rely on the phase matching issues. So you have phase mismatch due to the dispersion, but mostly in flat photonics, we are below the first coherence length of our material. Typically for lithium niobate or barium titanate is 2 micron. So everything below 2 micron, you don't need to do periodic polling, you don't need to invert your crystal here, as you can see that is possible to do on chip, and you stay in this region where there is no need of this kind of additional feature on chip. Though, so the second property that is also not available when you use silicon is electro-optic control. Here you have an example. I just wanted to show how to watch how you can apply an electric field, a DC field on a chip and change the refractive indices. So this is an example of a Mach-Zehnder interferometer or just a loop. And at the end of the loop, you have the reconstruction of the two beam, and they will overlay, and you have a kind of interferogram. And here what you can watch is how the interferogram is moving because you are applying a DC field, it's 0 to 20 volts, when you want to move the interferogram fully, but it's enough to have a few volts, like in CMOS compatible voltage. So this is the electro-optic control that you want to have on a chip, and the third property is entangled photon generation. So there, this is the workhorse of the generation of entangled photons since decades now with bulk crystals, where you have a spontaneous parametric down conversion, which is the opposite, mostly of, so to speak, of second harmonic generation, and you can have it also with the exact same material where you have electro-optic control or frequency conversion. Okay, on top of that, those materials, mainly those three materials, so you will really have to pick the right one depending what you want to do. If you want to do frequency conversion or electro-optic control, lithium niobate is a good choice because it has both the same strength, so 30 picometer per volt in the typical parameter that you can reach from the tensor. Then barium titanate is also now used mostly for the electro-optic properties because it has 2 orders of magnitude higher electro-optic strength, so 1000 picometer per volt also as bulk, compared to lithium niobate. And gallium arsenide, better not use it for electro-optic, there's no birefringence there, but for second harmonic generation or spontaneous parametric down conversion, as I will show you. So picking the right material is important. And the other properties that are available here are the large band gap for lithium niobate and barium titanate, 3 to 4 electron volt, from the UV to the mid-infrared. The refractive index slightly above 2, so this is enough to have a good confinement. And they are very inert, right? Those two materials are oxides, so they are difficult to etch, which means that the fabrication process is hard, but possible. So now, how do they exist? So, and how small quadratic material can be? They can be, so we know them as bulk, right? And we also know them as wafer, where with titanium indiffuse or proton indiffuse, you can reach mode area for the photonic integrated chip, for instance, on the order of 30 micrometer square. So it allows you to have 40 gigabit per second electro-optic modulation. This is good enough. But when you want to go to the new material that is now available since a decade as a commercial thin film that you can buy, then there, what you can reach is, with the exact same scales, right, a mode area of less than 1 micrometer square. And there we come into the sub-micron world, where we can think of doing also our nanostructures for flat photonics. And this field has really boomed lately, where we are now doing all kinds of on-chip sources for Bell state. And here, the entangled photon generation is really on-chip through the PPLN, for instance. And you can do, for instance, quantum key distribution on-chip as well. But this is not the type of topic I want to talk about, right? Is it possible also to use this kind of top-down fabrication to make flat photonics? And the answer is yes. Is it possible also to apply fields close by to have a nanostructure, to have enough field inside very little material? The answer is almost yes, I would say. So here you have an example of a flat photonic chip where we are applying a field with electrodes that are surrounding our nanostructure in lithium niobate. The target was to make pillars, but actually when you carve into a metal oxide, what you get is pyramids. And I will come back to that, how to get pillars and not pyramids. Anyway, with pyramids, those pyramids, we can get good resonances. And the principle of the electro-optic effect we're using here is the following. So we have a transmission dip with this structure that is resonant at a specific wavelength. And by applying a field with those electrodes that are surrounding our pillars, we can modulate our transmission signal over time. So how does it look like? So here we have the transmission dip of our system at 776 nanometer, and we look at the modulation enhancement here, the derivative of our transmission dip here. What we could show is that with a Q factor of only 140, because of the poor structure we are having here, so we had a modulation amplitude that is pretty low, and I will show you how to enhance this, but up to 2.5 megahertz with quite little applied field, so between 0 and 10 volts, or at 2 volts, you already see some modulation appearing in such kind of structure. So it's possible to modulate, and at a quite high frequency, up to 2.5 megahertz in that case. Now, how to enhance this moderate modulation by design, as we saw in the previous talk of Sasha. So here we are not only improving our fabrication, but we are using a design made by Antonella Vicenti in Brescia, and also it's a collaboration with the Politecnico di Milano, with the group of Michele Celebrano, where we were designing a grating, so lithium niobate grating, as you can see here. We were applying the field on the right, in the right direction, because you have a certain crystallinity on this material and you want the field in the right direction, with electrodes that are surrounding our grating here. So they're close by, but not that close still. They are just around the gratings. And when you do that, and you apply, you look at your light incoming on the gratings, in the right direction, you are applying your electric field, and you can modulate the frequency as well. So this is different from this work, right? In this work, from Dion and Brongersma, they are not carving into the lithium niobate the gratings, but they are just loading lithium niobate that is here in purple with metals and a structure and silicon structure. But we reach nearly similar properties here, which are the following. First of all, Q factor. So the Q factor of this grating are 8,000 at 1550 nanometer. And by modulating this structure, we are now achieving modulation, relative modulation of, now I need to go back, of 10% by applying just 20 volt. So this is possible now, and for up to 1.5 gigahertz, 1.2 gigahertz at minus 6 dB cutoff here for the modulation amplitude, or 700 megahertz at minus 3 dB. So you can have with a lithium niobate, so that kind of gigahertz modulation possible because of the type of material we are having, if the Q factor of your design is pretty high. Okay, so that's the top-down fabrication I'm talking about, and here you could see, right? So this was always a problem for us, that you could not really have straight side walls, and always those pyramids. Even when you look at the side walls of those Bragg gratings, they're also not straight. They're really bended. So the solution for that was to develop our own way of fabricating lithium niobate and not relying on the commercial substrate that are also quite expensive and sometimes difficult to get. So we are also working on solution-derived Ki2 materials. So those are, what we develop is barium titanate and lithium niobate solution-derived materials, and I will show you an example with those. There are other ways of getting Ki2 material, right? You can also assemble nanoparticle. Here is an example of those assemblies. But then you have a lot of scattering, and you will use this kind of scattered material for other purpose. There are also the spalling of barium titanate. There are also electro-optic polymer that have very strong Ki2 properties, as well as you can do pulse laser deposition to get barium titanate, for instance. So, the sol gel. So why would you do Ki2 material bottom-up? Simplify the fabrication, use other type of material, not only relying on the commercial thin films, and most of all is to have, it's very useful for nonlinear optics because you're relaxing the phase matching condition. Here, I'm talking about material that stays polycrystalline, which means that either a thin film or an assembly of nanoparticle, when you illuminate them with your infrared light, for instance, and you look at the second harmonic generated light, they don't depend on a specific orientation of your crystal, but your crystal is totally randomized. So even when we do a sol gel, we deposit the sol gel, we are not applying a field, so we have a totally randomized crystalline orientation, which means that you are in the case of random quasi-phase matching, and in random quasi-phase matching, it's a random walk, and you really measure second harmonic generation, electro-optic effect, and SPDC sources. The question mark here are important, because when we started working with those randomized crystalline structure, I got many times the feedback that you will measure nothing, why bother? But actually, because of random quasi-phase matching, you do measure things. And for instance, we can measure, okay, of course, in individual nanoparticles that are crystalline, you have a dependency on the polarization, and you measure second harmonic generation. and it follows the tensor that you're expecting down to a certain sizes. But when you have thin films, right, polycrystalline films, there is no dependency on the polarization. So your polar response is totally independent of it. And now when you start to structure your sol gel, of course you start to have again dependency on the polarization, so a complex polarization behavior because you have some structure and you start to have responses in your polycrystalline structure. Okay, so now we know that we can have nanoparticle structuring, sol gel structuring. The sol gel advantage is that we have very smooth structure, very little scattering. We have also a higher refractive indices because when you look at the refractive index of assembled nanoparticle films, it's below 1.8. When you look at sol gel material, it's close to 2. And when you look at the bulk material, it's 2.4. But 2 is good enough to make to have good confinement of light. And more important as well, I showed you that those sol gel, they have second harmonic generation, but do they have electro-optic effect as well? And yes, they do. So here you have, for barium titanate, the coefficient, the electro-optic coefficient. I told you before, this material is very interesting because the electro-optic coefficient is 1,000 picometer per volt in bulk. Though barium titanate is now done by MBE, and there the coefficient goes down 1 order of magnitude. And in sol gel, for barium titanate, what we have is a parameter that is close to 30 picometer per volt. I told you before, 30 picometer per volt is the parameter of bulk lithium niobate. So you have an electro-optic parameter in a material that is easy to fabricate with the same strength as monocrystalline lithium niobate. So this is interesting for electro-optic. And so the fabrication is easy. I tell that, right? So you go once to the clean room normally, and you do a master mold. Then you daughter mold, or in PDMS, you can use and reuse your master mold because this is soft nano-imprint lithography. And we just imprint our sol gel, barium titanate lithium niobate. It needs a calcination steps. So the only constraint here is to have a substrate that can handle this calcination step. And then what you get is nanoholes, pillars, fins, and I will close the loop afterwards to show you circuits. Dimension are small, below 40 nanometer, high aspect ratio, so we can make fins with 1 to 10 aspect ratio, very straight side walls, not anymore the pyramids that we were having before. And as I said, substrate independent. It's better if you can match a bit the substrate using magnesium oxide, for instance. But yeah, we do mostly on some sapphire or crystalline quartz as well. So what kind of device can we do? And why this is advantageous to master also the material itself is because now we can do very straight side walls, very periodic structure, where we can do color tuning, but most interestingly, not for second harmonic generation, but for electro-optic modulation. So this is a barium titanate structure. And now we don't need to put the electrode aside, right? We can make a conductive substrate below, on top, and we can put the electrode very close to the material so that the field strength inside your material that is already little is stronger. So that's the purpose. And of course, we have some, here we are still using resonances in that case. And what you get is, again, the modulation of this resonance by applying a DC field. And what we are measuring is relative modulation now that is on the order of 10 to minus 2 to 10 to minus 1. And before, in the structure where the electrodes were around the material, it was more like 10 to minus 3 to 10 to minus 4. So we gain 1 to 2 order of magnitude by placing the electrode much closer to the material, which is logical, right? And now there's another, we even reduce or try to have a better overlap with the optical field and the electric field by even decreasing the amount of silicon dioxide we have surrounding our material. Right here you see the electric field is still mostly in the silicon dioxide, so in the cladding of your material. And the material is there. So how you can do that is by etching down your cladding and having an embedded configuration, and you increase your electric field inside the barium titanate, so the material that is electro-optic, right? Or you can even do a conformal configuration so that you have even stronger electric field inside your material. So this is a way of getting improvement by a factor of 3 of the efficiency of the material, and also a modulation speed up to 5 megahertz. So you don't gain an order of magnitude, right? Only a factor of 3. But yeah, this is then you need to apply less field to have the exact same properties there. So playing with the design again. Okay, now barium titanate was the easiest sol gel material that we could fabricate, and then we say, oh, if we can do barium titanate, you can do lithium niobate. A bit more difficult. Lithium is light, so it's volatile. You have to have good glove box so that you can do that, but it's possible. And when you have then lithium niobate, what is interesting to do is not electro-optic, because electro-optic you're going to dilute the 30 picometer per volt even more, but also it's interesting to do also frequency conversion. And here, so this is the example of a lithium niobate sol gel metal lens, where we have fins that are very nice compared to the one we could get when you do top-down approach. Okay, the material is very regular. Here you see the polycrystallinity of the material, which looks pretty good inside the fins, actually. And by doing either rectangular unit cell or triangular unit cell, with the material itself, you can get the focusing of the fundamental light, as well as the focusing of the nonlinear light, thanks to the high aspect ratio of our material that we can get, so we really have this half-wave plate effect. Okay, so yeah, so this is the what I wanted to say. So it's different from this kind of structure, because we are here using just the non-resonant, so the geometrical phase, which means that we can really focus with the same structure without having to care about the wavelengths, wavelength that goes from 400 nanometer to 800 nanometer. So we are really non-resonant and broadband here. We are missing those points because our laser died between those two measurements, or part of the laser, so we just have one had to change the laser. But yeah, that happens. Huh? Okay, now I'm closing a loop, because we were thinking, okay, we can do a flat structure. What about circuits with the sol gel? Because that would be cool, right? So you imprint circuits, and we can do that. You see now, so this is a 15 by 15 nano imprinted chip. What you can see, so you see how, because we spin coat the sol gel, right? We spin coat barium titanate, and then directly after spin coating, you imprint. And here you see a circuit already. Close by view, we are having cut back structure just to measure the losses that we are having in those circuits. And you can also have a look at the grating coupler here. So we are just by nano imprinting. And the nano imprinting is not done with a machine. We do it manually in our gray lab currently. We have a kind of a technique, but it's really something manual. It's not something that we are doing roll to roll on a kilometer, like Jeremy was saying before. So yeah, so here, but the structure are good. I'm always reluctant to give the losses. They are for sure not as good as in silicon or silicon nitride, but we are pushing down the losses currently in those photonic circuits. And we have a first demonstration of a modulator with this barium titanate sol gel circuit. So this modulator, what is nice, and then I come back to the fact that we have a random-oriented crystal, you can put the electrode anywhere. Now you don't need to follow the crystal orientation, because there is no more specific crystal orientation. So wherever your electrodes are, if you have a weird design or probably a racetrack or so, you can put the electrodes there, and you can profit from the electro-optic coefficient. Okay, so I showed you top-down fabrication, sol gel fabrication, and there's one last short part. Just wanted to mention also that Chi2 material are suited for direct generation of entangled photon with the material itself. With the example of gallium arsenide nanowire, I hope you did not miss the talk of Elise by Riofrey yesterday, because she talked about this system. So this is a zinc blend gallium arsenide nanowires that are grown by our collaborator in Lyon. That's how they look like. And we transfer mechanically them on substrate. We can also micro-manipulate them to put them in the way we want. And here you have a perfect, more or less perfect arrangement of perpendicular nanowires. And we are profiting from type 0 spontaneous parametric down conversion in those perfectly perpendicular nanowire, in which we can generate really idler and signal with the same polarization. What we're exploiting here by using gallium arsenide is the very high Chi2 coefficient of gallium arsenide, right? That goes up to 300 picometer per volt, so that we don't need to wait a week to get our entangled photon generation from this nanostructure. Okay, and here is the results of the Bell state generation from when we are illuminating our gallium arsenide cross nanowires with polarization that is along the diagonal or this is the anti-diagonal axis of our nanowire. And what we could get is a fidelity as high as 90% just by having this kind of arrangement here. So very simple setup and structure on chip. Okay, so I like to conclude here. I hope I showed you that with Chi2 material you have a zoo of experiments that you can do, either in top-down crystals. So here you have our example of you have our example of a top-down crystal for modulation that you can use for electro-optic effect. I didn't talk about optical computing, but now we are using the non-linearity of a Mach-Zehnder modulator on chip, and also the non-linearities of lithium niobate to make optical computing on chip. And of course, I think bottom-up sol gel is really a promising material that we can exploit, not only for flat photonics, but also for integrated circuits if we can bring down the losses. And that's what we are working on right now. And of course, now we have entangled photon generation in gallium arsenide, but you could, of course, we already have entangled photon generation in lithium niobate monocrystal, but now we are trying to show that we can have also this kind of photon generation in random-oriented crystal as well. I thank you for your attention, and yeah.
Thank you very much for the wonderful conference.
Rachel, a great talk. The second harmonic generation all of a sudden has become a very popular topic because of quantum devices, of course, and your talk is a great example of that. In nonlinear optics, it's very well known that if you have two non-collinear beams which are circularly polarized, they can generate second harmonic in isotropic system, which is chiral. Chirality, of course, strongly depends on how large your molecule is. And metamaterials allow you to operate with molecule of every size. So because of this optical activity, chirality, and its manifestation in metamaterials is very, very strong. So my question is anybody looking into a chiral version of second harmonic generation?
I think, yeah, many people are working on chiral. We are not, but
it does not require material with lack of center of symmetry.
Yeah.
It only requires chirality, which is a very different condition. It's up a different...
So we have looked into chirality in silicon germanium structure that were spiral already.
Yeah.
And there it's non-central symmetric, and you can show that you have chirality and that you have second harmonic generation because of the non-central symmetry.
Experiment. It must be non-collinear, otherwise it's something else.
No, there it was a single beam experiment. It was not a beam experiment.
So, well, my suggestion is maybe this is a promising thing to do.
Okay, thank you.
Rachel, thanks for the nice talk. I have a question. So in this sol gel process, I see you have more knobs than just crystal growth. So can you affect significantly coherence length, for example? Or have you tried measuring that in your sol gel films?
I don't think you can affect coherence length because it will depend on the material itself. You can affect electro-optic properties. You can pole the sol gel, actually.
Right, but because you have porosity and also the chemistry, maybe you can affect the indices, and then your coherence length can change. So is that significant?
So you can do polling for sure.
Without polling.
Without polling, just by
controlling the chemistry or doing. Right.
Well, we don't mix two chemicals to make different polling in itself because it's totally random what we get, right? So, but yeah, that's a good point. So maybe something to try.
Talk later.
Maybe something to try.
I had a quick question, just of interest. Very nice work. What is the insertion loss of this salt gel structures? Because the on-chip propagation lengths and also the sidewall roughness are killer in most of the materials on chip.
For sure. The insertion loss.
Whereas lithium niobate is known to be the lowest loss material for nonlinear optics.
So we are not at the 0.2 dB per centimeter transmission loss of lithium niobate. Currently, we have brought down the loss from 40 dB to 10 dB per centimeter. So the transmission loss plus coupling losses, of course. And the coupling losses, they are similar, right? It's 3 to 4 dB because the grating coupler, they are pretty good. So they are as good as the one you can get for silicon nitride. But most of all, the transmission loss are still pretty high compared to silicon nitride. So we are at 10 dB per centimeter loss. We need to bring that down for one order of magnitude if we want to be a decent photonic integrated material. So that's why currently it's suited for flat photonics rather than peaks, but we are working on the material to bring down the losses. It's smooth, the walls are super smooth. I think it's really the scattering because the grain size are 50, 60 nanometer grains. Yeah.
Well, thank you very much, Professor Grange. Before we go to the announcement.
Please.
Let's thank all the speakers this session and thank audience.
Oh. Okay. We're not quite ready yet because there is an important. Can you?